The broadcast is now starting. All attendees are in listen-only mode.
Hello, and welcome to the Acculon NanoClear webinar. Today we're going to be discussing the application bulletins. Acculon is the producer of the #1 global stencil nanocoating, NanoClear. My name is Edward Hughes. I'm the CEO of Acculon, and we are the producers of the NanoClear. Joining with me today is Chris Shea, the president of Shea Engineering Services, an independent consulting firm that specializes in the SMT industry and print processes. Chris has nearly 30 years of experience in improving processes, and for the last 5 years has been leading the independent study of nanocoatings and the improvements that it can make in your processes. Today's agenda is I'm going to give you a quick overview of Acculon and talk a little bit about what the stencil nanocoatings are. Chris is then going to take you through 12 technical bulletins that address specific questions that customers have asked over the last 5 years. I'll wrap up with a quick summary and then we'll dive into questions. This recording will be available for download. We'll be sending an email with a link to not only the recording but also to the presentation itself. So you'll see in your control panel that you'll have a box for any questions. As your questions come up, please type them in the box. We'll try to address as many as we can as we go through the webinar, and then we'll address any other questions at the end of the webinar. So firstly, what are stencil nanocoatings? Well, they are extremely thin flux repellent films that are applied to the bottom or the underside of the stencil and also coat the aperture walls. When I say extremely thin, we are talking about 2 to 4 nanometers thick. Flux repellent, obviously they are designed to repel the solder paste from getting clogged in the apertures or sticking to the underside of the stencil. And after 5 years of doing this and probably 500,000 applications to stencils, we have very good customer data that indicates that we consistently improve print quality, we get higher yields, we improve what we'd like to call the transfer effectiveness, and we'll be discussing what exactly that is during this webinar. We boost productivity, and that's driven by you can wipe the underside of the stencil less frequently when you have a nano coating on this, and also allows you for less downtime due to paper changes, because obviously you're wiping less frequently. And finally, and as important, we reduce costs. You'll see that we have a great track record of improving yield. That means that you have less rework to do, and then also from a consumable perspective, lower paper and solvent consumption basically pays for the cost of the NanoClear coating. And so this is why that NanoClear has become the #1 global nano coating. We are very fortunate to have some very high-profile blue-chip companies using our products, and some of them are listed on this page. We are also very fortunate to have some key assemblers using our products, and again some are listed on this page. And as many of you know, early on we partnered with DEC, or what is now part of ASM, to help us distribution on a global basis. The product has been in the marketplace for a number of years, and we have picked up a series of awards, whether it's Circuits Assembly's New Product Introduction Awards or whether it's Global SMT Awards. We've been fortunate to be certainly well recognized for that. We've also had numerous technical articles that have been printed in well-respected publications, and we've been featured on the cover quite a few times, and a couple of examples of that are shown here. So this is a product that has been around and very well respected, and certainly highly decorated. As it comes to distribution, we in Acculon are based here in San Diego, California. We handle the North American and South American market directly from here. We have partners in Europe with CapLink, and they handle all of the European marketplace. And then in Asia, we have distributors in many countries, including Korea, Taiwan, China, Malaysia, the Philippines, and Australia. And I also, as I say, the Aculon NanoClear product is available on a global basis from DEC. So hopefully we can cover all the key marketplaces to make sure that we can get the product into the hands of our customers. So what we've done for this particular webinar is we've basically, with the 5 years of experience we've had with working with PCB assemblers, we have tried to look at what kind of questions they have and put those into technical bulletins so we can address some of the key things that questions people have. So we've created 12 of these. And what we're going to start with is basically each one of these is going to be a quick presentation that Chris is going to share with you. But we'll start with just explaining what the difference between a wipe-on coating such as NanoClear versus some of the spray-on coatings that are starting to appear on the market. We will then address questions regarding, is NanoClear going to contaminate the solder paste or pose a reliability risk to solder joints? One of the questions we often get is, does it coat the aperture walls? We'll share with you a study that validated that it does coat the aperture walls, and obviously that's part of the reason you get the printing benefits you get from this. The next question is, how long does it last? And we'll give you some indications of what customers have told us, and it's the answer. It is going to come down to, it depends a little bit on the printing conditions and parameters. But we'll then share with you, well, how do I check that it's still there? Because obviously when you're 2 to 4 nanometers thick, it's basically you can't, it's an invisible coating. And then we'll give you some methods or techniques for how do you improve the durability or longevity of the coating by using things such as softer underwipes. Then we'll go through how else can I improve my print processes. If you're already using NanoClear, what is the benefit of adding things like an engineered solvent? And then we'll dive into a little bit around, well, how specifically does NanoClear improve print quality? And then how do you measure this, in terms of this phrase we use, transfer effectiveness versus transfer efficiency, and explain a little bit of the statistics behind this so you can understand what key statistics are important in measuring print quality. And then we'll wrap it up with what some of the other process benefits of NanoClear, and then how can we demonstrate cost savings. And we have an online calculator that can basically demonstrate that for you, and Chris will walk through some of that. So with that, let me turn it over to Chris, and as I say, she's been studying this for last 5 years on an independent basis and is an expert in this area with her 25 years of experience. So she's going to take you through each of these technical bulletins and explain what's going on. Chris, let me hand it over to you.
Thank you, Edward, and good morning or afternoon to everybody who joined us today. As Edward said, I'm going to be going through about a dozen of these technical bulletins that we put together. These will all be available individually off the website if you want to download them on an ad hoc basis. I think everybody will receive a copy of this presentation as well. The first question, and also I want to mention, as Edward said, these bulletins are based on the questions we've been answering coming in from the customer base over the last 5 years. There's a common core of questions here, and that's what we're addressing. So one of the major questions we always get is, what is the difference between the wipe-on and the spray-on nano coatings? Because they seem to compete with each other, but I think actually has its own place in the marketplace. The spray-on nano coating is a fluoropolymer that's sprayed on and thermally cured by the Stencil supplier. The NanoClear is a wipe-on self-assembling monolayer phosphonate, or SAMP material. We'll talk a little bit more on the next slide. That can be that's simply wiped on. It takes only a few minutes to apply, and it can be applied by your Stencil supplier or in your own facility. So the thickness on them is a little bit different. The fluoropolymers are in the micron range of thick, 2 to 4 microns. The NanoClear is in the nanometer thick, so 1 to 2 nanometers. I think we've measured it as thick as 5 nanometers. Both of them are hydrophobic, which means they repel water, oleophobic, which means they repel oil, and fluxophobic, which is most important to us, meaning they repel flux. Both have good abrasion and chemical resistance, and we'll show you in a few more slides what some abrasion resistance tests revealed to us. Chemical resistance, they all prefer pH neutral, or at very least pH less than 9 to avoid being attacked. The spray-on fluoropolymer is tinted, so it's visible. Sometimes it's a colored tint, sometimes it's a UV tint, but it is visible, so you can see if it's coming off the stencil and where it's coming off the stencil from. The SAMP coating is not visible because it's only a single molecule thick. There would be nowhere to actually attach a dye molecule into that coating. When it comes to rework, these can be scratched, abraded off, or attacked by high pH or low pH solvents. The fluoropolymer cannot be reworked. If you have a wear issue with the SAMP, you can simply apply another packet. The fluoropolymer is available through selected suppliers. The White Bond or NanoClear is available through selected suppliers, or straight through the internet if you want to buy it directly from Aculon or one of their distributors. Both coatings dramatically reduce the frequency of underside cleaning. When I say dramatically, I mean, in my experience, almost a 2x increase. So if you were wiping every print because you had a really difficult board, you can now wipe every other. If you were wiping every 3 prints, we've had people get better results with NanoClear wiping every 5 to 6 prints versus without NanoClear wiping every 3 prints. So I typically tell people to extend their wipe intervals by 50 to 100%. We see differences in solder paste volumes or transfer efficiency. The spray-on fluoropolymer has shown increases in transfer efficiency, especially on area ratios less than 0.66. On the NanoClear with our SPI machines, we actually see a slight decrease in measured transfer efficiency. I believe some of that is due to the algorithms of the SPI machine. What we find with a NanoClear is a very crisp, straight-walled print. We don't see that slumpy lower part of the print that can actually cause some SPI machines to give higher readings than normal. If you want more information on that, we have it in a different webinar because it gets quite detailed. For smaller apertures with a spray-on fluoropolymer, you may need to do a little redesign because if you're getting too much increase in transfer rate, you can risk bridging on your smaller components. Because we see very similar transfer rates or a measured slight decrease with a crisper print on the NanoClear, we don't recommend any aperture changes at all. The spray-on fluoropolymer can push your area ratio. We've seen in tests that we can at times go from, say, our bottom line was a 0.6, we can bring it down to a 0.5. And we can see that, I'm sorry, that just went forward on me. We can also see that we do get slightly better release on the lower area ratios with the fluoropolymer, but again, we have to be a little careful about that. Again, on the NanoClear, we get the same as the foil. We don't have to change any apertures at all. The cost of the fluoropolymer is a little more expensive. It's about a $100 cost adder to the stencil, and that depends on the supplier itself. The White Bond or NanoClear SAMP nano coating is as inexpensive as $20 if you're buying it direct. If you're having your stencil supplier put it on, they will likely charge you an upcharge for putting it on, so we would estimate a maximum of $50 for that. So that is basically the difference. We're going to focus more now on just the NanoClear itself. And one of the biggest questions we've had is, can NanoClear contaminate solder paste or pose a reliability risk to the solder joints? Well, it's been applied to over 500,000 stencils in the last 5 years. It's produced, by conservative estimates, over 1 trillion solder joints, and we have not had one reported NanoClear related failure. given how involved I am in stencil printing and research in stencil printing and pushing the limits for miniaturization, I can only assume that if nanocoating were being blamed for joint failures, I'd have heard something about it by now, and the nanocoating manufacturers would have got wind of it by now, but we have not had any reported failures due to a nanocoating on a stencil. And why don't we have any problems? Well, this is only 1 molecule thick. It cannot flake or chip off. It leaves no residue. It's not ionic. So we are not going to see any contamination in our solder joints. We're not going to see any ionic residue in them that can cause reliability issues down the road. So we believe it's pretty inert once it's on that stencil and pretty safe and secure. Now the SAMP molecule itself, we have a quick sketch of it here. This is your stencil, and the phosphonate head group is what bonds to the stencil. Many of you have probably seen this diagram before. The phosphonate makes metal oxide bonds with the stencil oxide layer itself. They're very strong bonds. We have a little bit of cross-linking, and then up here we have what we refer to as the functional tail group, or what a non-chemist might call the business end of the molecule, and that's what acts as a flux repellent. Now, there's also been a lot of questions, does it coat the aperture walls? Because those of you who've used it or have watched the videos online see that we just wipe it on from the PCB contactor, the bottom side of the stencil. And how can we prove that it's in the stencil aperture walls? Because we can't see it, and because it's so thin we can't see it in a standard cross-section, and because there's no tint we can't see it visually. So what we have to go to see it on the aperture walls is an analytical method called transmission electron microscopy. So the TEM analysis did verify that it is there. There's a rather large study that shows the stencils before coating, after coating, and after 15,000 print cycles and 5,000 IPA wipes. What we've got for you here is just a simple sample of what's in the full report, which you can download. And to be able to see the coating, they have to first cover it with a carbon-based ink and then plate it with, I believe it is platinum. So what we see on the left is the uncoated stencil wall. You see a very fine line of the carbon-based ink, and then you see the platinum. Now, the carbon-based ink sounds like a very technical material when used in an analytical lab. It actually comes from a Sharpie pen. And any of you who's used NanoClear know that Sharpie pens beat up on NanoClear. So what they have to do to detect on the NanoClear on a coated stencil is actually first plate with chromium, then put the carbon-based ink down to give them a differentiation layer before the platinum. So what we see here is stencil. This light stripe that we see right in here is actually the NanoClear. You can see some of the measurements here. It's 0.99 nanometers, or 1 nanometer. Here it's 1.4 nanometers. Here it's 2 nanometers. Other parts of that section showed it up to like 4.8, 4.9 nanometers. So we're confident in saying that it runs 1 to 5 nanometers. After the NanoClear, we then see a faint line of, we see the chromium, and then we see a faint line of the and we see the palladium, I'm sorry. So anyway, the takeaway here is, yeah, uncoated stencil, we don't see anything on the sidewalls. Coated stencil, we measure it between 0.9 and 4.76 nanometers thick. It really is a nano coating, and it is present on the walls. It was also present after the 15,000 print cycles. If you're really interested in this, it's a very technical presentation. I would encourage you to go to the website and download it. If anybody has any questions, please just type them in at any time. Another question we've had a lot is, how long does NanoClear last? And it's a difficult answer because there's so many factors that go into it. One is the abrasiveness of your wiper paper or wiper fabric. Another is how often you're wiping. A third is, are you using a solvent wipe or a dry wipe? Another factor is the pH of the underwipe and offline cleaning solvents. And just a note on that, in addition to considering the pH, and most of the solvent manufacturers, the Zestrons and Kaizens of the world, do have pH neutral cleaners. It's never a good idea to leave a stencil in a stencil cleaner overnight. We see that a lot in factories and some of the labs and some of the low volume places. It will, you know, you don't want to soak your stencil in solvent for a number of reasons. Yeah, after a good 8-hour soak you may attack it, but you're also going to delaminate your epoxy bonds and make them weaker. So don't ever leave a stencil in a stencil cleaner overnight. It's a common practice. Another factor is solder paste chemistries. Solder paste chemistries do have a lot of interesting chemicals in them, particularly the water solubles. I don't have data on it, but I have a lot of observation and empirical experience that says water solubles do tend to attack any kind of nanocoating faster than no cleans. And one thing that we also see as a factor is the wiper pressure against the stencil. How do we measure wiper pressure against the stencil? Well, it's not easy. I think what we need to do as an industry is look into this a little bit more and perhaps set better travel stops and the z-axis on the wiper. Because if you go from one machine to another, you'll see one wiper barely contacting and you'll see another one pushing up through. So we need to calibrate our machines a little better in terms of the wipe stroke, the underwipe stroke. Some of the things we can do to enhance NanoClear durability: use those softer papers. Examples of the less abrasive papers are the Deck Eco Roll, the HyperClean P4200, or the NanoClear micro wipes. These are softer papers, they're gentler papers. You no longer need a really abrasive paper like you do on a coated stencil, on an uncoated stencil. Uncoated stencils, the flux tends to stick and you really need something to get in there and scrub it. These coated stencils, the coating is a little soft, but the flux and paste comes right off of them, so you don't need to get in there and scrub it. If you extend your wipe frequency, you'll be abrading the stencil less. And because you're using NanoClear, you can extend your wipe frequency. If you're using a solvent wipe, that provides some lubrication to decrease the abrasion of the wiper textile that you're using. Again, higher wiper pressures will increase the abrasion factor. Again, I don't think there's any real setting on printers for wiper pressure. It's just a matter of setting the height of how far it drives up into the stencil. Again, we said pH neutral or pH less than 9 on solvents will not attack most nanocoatings. Solvents with pH greater than 9 will attack both your wipe-on and your spray-ons. And even if you're at pH under 9, don't soak your stencil overnight. If you're looking for signs of wear for any nanocoating, look at the end of the underwipe stroke, because where the wiper disengages from the stencil, it leaves a little bit of flux behind, and that's the first place you'll see the degradation starting to happen if it does. So it's a good process indicator. You can keep your process in control regardless of what nanocoating you're using. If you're checking with a Sharpie or a dine pen the area where the wiper disengages, you will place or rework that nanocoating before your process runs out of control, and that's the whole point. How can you tell if it's still there? Well, on the production floor, it's pretty easy. And again, most users do report about 25,000 prints. It depends a lot on the process, but that's pretty much a good norm. On the production floor, Aculon provides dine pens that have dine fluids in them. They're like little magic markers. It's dine fluid. The fluid wets to the untreated surface, as you can see on the left. Right here, it just wets and spreads. And on the right, you can see it beads up. This was actually, we masked one half of the stencil. We coated this half. We didn't coat that half. You can see the difference in terms of wetting from that dine pen, and we're also going to show you prints from both sides of that stencil. Now, if you don't have a dine pen, like I said, you can use a Sharpie, because the Sharpie ink has around a similar surface energy, so it will bead up for you. It's not as precise, but most engineers do have Sharpies in their lab coats, so if you're out on the floor and you're questioning your nanocoating, pull out your Sharpie. Now in the lab, we use oil contact angles or water contact angles, which is basically a very simple test of dropping a known quantity of water or oil onto the stencil and measuring the contact angle with a device called a goniometer. The lower angles we see on the left, or the more spread of the water or oil, indicates lower repellency. On the right, higher angles or less spread indicate higher repellency. So this might be similar to a car before it's been waxed or a car after it's been waxed when rain beads up on it. It's very similar to how the NanoClear works. But again, this is a laboratory test. Not everybody's got a goniometer to measure contact angles. So on the production floor, it's easy enough to use NanoClear's test pen or a Sharpie. Now, we talked about using softer underwipes in an earlier slide. And why do we want to use softer underwipes? Well, because the more abrasive ones may damage the coating. I mentioned that uncoated stencils require the harsh papers, but stencils coated with NanoClear don't need harsh papers. They actually should use softer papers. An analogy I like to use is cookware. Everybody has frying pans or pots and pans in their house that are either coated with non-stick surface like Teflon or Silverstone or not. They're just aluminum or stainless steel. You can use a Brillo pad or some type of steel wool to clean out that stainless steel pan, but if you take it to a Teflon coated pan or a non-stick pan, you will tear the coating right off. It's not quite as drastic with the nano coatings that we put on stencils, but it's a very similar analogy. You don't need the harsher wipe. You can damage the coating, use the softer wipe, and you won't damage the coating, and it will last a lot longer. So, in the lab out in San Diego, the fine folks at NanoClear have run some abrasion tests on a benchtop tester out to 70,000 simulated wipe cycles. And the way they simulate the wipe cycles is by using, again, a benchtop abrasion tester with a mass on it similar to the pressure that we calculated on a standard stencil printer underwipe, and also lubricated it with a very common flux. So what we see right at the beginning, the time zero contact angles, NanoClears are very consistent. They're around 90 degrees. And as we run through the wipe cycles, 10, 20, 30, 40,000 wipe cycles, NanoClear with a highly abrasive paper, one of the most popular papers for non-coated stencils. You can see how it gets abraded down, and if we say 60 degrees is the minimum contact angle for good flux repellency, that takes us down to almost 40,000 cycles. If we are using the softer paper, we are good well out to 70,000 cycles. Much better. Now if we look at the fluoropolymer with the two different types of papers, this is very interesting. Two different areas of the same stencil came up with two different, very different contact angle readings. The fluoropolymer does not appear to be as affected by the harsh paper versus the soft paper. The solid line again is the soft paper. That follows a fairly similar trend line to the NanoClear in terms of just sort of a linear mild degradation. The interesting here is the fluoropolymer with the abrasive paper. Now these came off the same stencil, but this one had a much higher contact angle, so we can make several assumptions about it. Perhaps it was thicker, perhaps it was a little more cross-linked, we're not really sure, but it stayed pretty steady. This is a trend line, so it shows a little bit of a curve, but if you looked at the scatter plot, it's pretty linear. It's just pretty steady. It fell off at the end, but we did not see it as susceptible to the abrasive paper, but again we had two samples off the same stencil that showed very different time zero or cycle zero starting contact angles, so it's a little puzzling, but both of these did run out to 70,000 cycles and stay above our goal, and the NanoClear obviously went out 70,000, also stayed above the goal, but with the softer pocketed paper, and that's long-term repellency, if we look way out here, if we're using NanoClear with softer pocketed paper, we're getting a lot more cycles out of it without degradation, and we don't have a sort of disparity at time zero that we can't really explain. So that is the whole story of why we want softer underwipes, and that is the data behind why we suggest softer underwipes. How can we further improve our print process if we're using softer underwipes? Well, we can add engineered solvent. Studies we performed with a paste manufacturer showed that the combination of nano coating and engineered solvent gives us the best-in-class print process. So we dubbed that the double play. After a baseball analogy, of course, after Sunday's Super Bowl, I'd like to dub it the two-point conversion or the double two-point conversion. Anyway, here's what we see with a dry wipe. We have a nano-coated stencil. We have flux that's been treated with UV dye. And after the wipe, we can see our apertures are pretty much clear, but we definitely see flux smeared on the bottom of the stencil a little bit. Now with the IPA wipe, this paste was very IPA unfriendly, and this is not uncommon in the world of lead-free solder paste. In the world of tin lead solder paste, IPA was a great wipe, and it dissolved almost everything. In the world of lead-free, it's not the alloy, but it's the fluxes that make it more difficult to clean. So IPA, you can see we actually clogged apertures that were 6 or 5 mils wide and smaller. You can see we clogged a lot of apertures in the round and square areas. They're a lot more obvious in the rectangular areas, but yeah. And we have a lot more flux smears on the bottom of the stencil and clogged apertures. Now, this is with NanoClear and an engineered solvent wipe. We have no flux on the stencil. We have no clogging in the apertures. So this is why we say if you really want to get the most out of your printing process, add the engineered solvent wipe. A lot of people are still dry wiping. There's been a lot of controversy over whether solvent is better for the process or not. We're not showing the data in here, but we published data last year at SMTAI where we did a solvent wipe, and it showed a much more stable process. That was actually a study I did with Kaizen, not with Aculon. Now, how can you check your solder paste compatibility with underwipe solvent? Extrude paste into little glass beakers or sample jars containing the solvent. So you see this is IPA. What I did was I went to the local pharmacy, got a medicine syringe, and just squeezed paste through the syringe into the little vials of IPA, or I use little glass jars. And you can see this lead-free paste was fairly soluble in IPA. This one was fairly soluble in IPA. These three just congealed. So I said the fluxes in lead-free solder paste are a lot more complex than what they were in tin lead solder paste, and many of them are not fully soluble in IPA, as we found out when we did this particular experiment. So now, when we say how does NanoClear actually improve my print quality, well, what I've seen and what many people have reported are much lower print variation. We'll talk about print statistics in a little while. We see a lot less peaking or dog ears because as the stencil and the board separate, we don't have that tug-of-war going on where the paste is getting pulled. The stencil is just letting go of it. So we see much better, crisper print definition, and we see reduced underwipe requirements. Now, a few tech bulletins ago, I showed you a picture of a stencil where we coated half with NanoClear and left half bare. This is the stencil, and these are the resulting prints. This is a 0.5 millimeter QFN in here. These are 0201s. We did 10 prints without a wipe. On the uncoated stencil, you can see all the flux bleeding out around the apertures. You can see apertures already bridged, and anybody who's been printing for a while knows that the solder spheres follow the flux. So once that flux is wetted out, we're going to have a bunch of little solder spheres and powder on the bottom of it. Now, this is the same stencil, 10 prints without a wipe, just on the coated side. The difference is amazing. You do not see nearly the flux bleed out on the bottom side of the stencil that you see on the uncoated side. You'd still see flux on these big webs in here because there's a lot of deflection that goes on at separation when you have a big span like that. So that's pretty normal to see more in there, but again, it's not nearly as much. So part of the reason we don't have to clean as often with NanoClear is because it repels the flux and it's easy for the paper to pick up. But the other reason is we just don't get this bleed out. We just don't see it. You just don't need to clean as much. And when you do need to clean, it comes off really easy. It's, again, the Teflon frying pan versus the stainless steel one. Now, if you look at the resultant print, it's a little hard to tell on the O201s if these are crisper than these. It's a bit subjective. And these look a bit crisper than these, but the real tell is right here in the ground pad. You can see what looks like a slumpy print versus what looks like a crisp print. You can actually see the bridges forming right in here on the slumpy print. Why does this print look so much slumpier? Well, because you've got so much flux and paste out around the apertures. It's a lot stickier at separation. It's a lot harder for that to pull out, and that's why we end up with a print looking this way versus a nice crisp print looking this way. And I've got another picture coming up on a few more QFNs that are really, really spectacular. Here they are. So this is where we talk about the difference between transfer efficiency and transfer effectiveness. For years, we've all looked at transfer efficiency as the total volume of solder released from an aperture. We express it as %. It's measurable. It's quantitative. All our SPI machines give us data in terms of transfer efficiency %. But now what we really need to look at as an industry is transfer effectiveness, not just how much paste you put down, but what's the shape of that paste deposit. Is it dog-eared? Does it have strings causing little wet bridges? Is the volume variation too much to handle? So let's look at, now we're looking at a 0.4 millimeter QFN that came off a production line in Asia. Now, before coating, we can see kind of big prints here. After coating, we see very, very crisp prints here. So we've got a lot of excessive paste volumes here. We're begging for solder bridges out in some of these areas. There's a lot more volume variation, and there's just a very poor shape quality there, so we have a high risk of solder defects. On this one, we have more appropriate paste volumes. They're crisp, they're contained within the pad, they have less variation, and they give us much lower risk of solder defects. Now, incidentally, this print was getting wiped every 3 prints. After nanocoating, this is where we bumped it to every 6 prints, and we're still getting higher CPKs, lower print variations. So these are very telling pictures. Now, why is this important? Because more paste isn't always better. When we began fighting miniaturization many years ago, we're always looking for the best transfer efficiency out of a small aperture. I dare to say that's not the case anymore. If you think of a micro BGA or an O201, you're running with typically, and I apologize for you, up 400 cubic mils of solder paste on the I/O pads. If you get a 25% volume bump because of a nano coating, you're now running 500 cubic mils of solder paste, and you can see short solder balls, tombstones, excessive skewing, anything, all of which require rework. So on miniature devices, we want to hit a target amount. We don't want to just say more is better. So here I see us hitting the target amount, which is a much tighter distribution, a much lower variation, a lot less risk of solder defects on the coated one than the uncoated one. Incidentally, I believe this was the same stencil. We pulled it out of production, coated it, put it back in, and bumped the wipe interval from 3 to 6 all at the same time. So that was pretty stunning. That's telling. Now, let's talk about statistics for a minute, print statistics. This is not an easy bulletin to put together because it's difficult to explain statistics, never mind write them down. But there's a couple different metrics we use in our industry. We always look at transfer efficiency, obviously, or volumes, but we have to look at the spread of the data or the variation in the data. So we've got CP, which is the Process Capability Index, and that tells us what our process variation is in relation to the limits on our specifications. Now, when we go to CPK, we look at the same thing. What's the process variation or distribution of the data with respect to the spec limits, but also, is it centered between the spec limits? And finally, CV, which is really my favorite, the coefficient of variation just relates your variation to your average, and it takes your spec limits out of the equation completely. So all these metrics are based on standard deviations or sigmas to describe the spread of the data, and they all use them a little bit differently. So it's very important in here when we talk about statistics in the context of print data that we have a good handle on these. CP describes the shape of the bell curve. Is it short and fat, or is it tall and skinny? We want the bell curve to be tall and skinny. So what we do is we take the range of spec limits. Typically in stencil printing on your SPI machine, your default tolerances are plus or minus 50% of the theoretical aperture volume. So your upper spec limit would be 150% transfer, and your lower spec limit would be 50% transfer. Looking at this, some of your data is going to be out of spec, so you're going to create rejects. Looking at the shape of this, your range of data is well within the range of your limits, so you have this high CP. This is excellent. It doesn't address the average at all. Now, if we go to CPK, what this does is it breaks the spec range in half to determine how well the distribution is centered. So instead of just going for the upper minus lower spec limit, or the whole range over 6 sigma, it says, all right, upper spec limit minus my target over 3 sigma, or my target minus the lower spec limit over 3 sigma. So now what it does is it breaks into 2 halves to tell us if it's centered or not. Here we would have a low CPK, obviously, but we are centered, but we're out of the spec limits. Here we have a high CPK because we're centered and we're in our spec limits. Here is where we run into a lot of issues when we're interpreting our SPI data. Here we have the tightest distribution of all, so we would have a very high CP, but because we're not centered and a little bit is squeaking below the spec limit, we would have a very low CPK. The reason this is a problem is many of our SPI machines automatically center on 100% transfer efficiency. They go plus 50 to 150, they go minus 50 to 50. But as printing professionals, we know that when we get in these tight area ratios, we're likely to release 80, 85, or 90%. We're not going to release 100%. If we were always releasing 100%, we probably wouldn't need SPI machines. So our SPI can actually give us a bad CPK reading because it's not centered where our process is centered. Some machines will let you change this, others won't. A lot of them actually just calculate CPK based on a 100% transfer efficiency goal. And if we know our best day we're only releasing 85%, we don't have a very good statistical setup. Now, we have actually had cases where because we drop on our transfer efficiency measurement by 2 to 3 points, but decrease the distribution, CPK has gotten down. And people have rejected the use of NanoClear because even though the distribution is tighter, it's shifted a little bit more to the left or to the right, and it's shifted away from the 100% that the SPI machine is looking for. So this is a very tricky thing here. I really, really try to avoid, CPK is great in production, but if you're running tests or developing a process or comparing different print studies or print qualities, it's not the best choice. I like CV because all it does is take your standard deviation and express it as a % of your average. So spec limits are completely off the table. If I'm doing, this is a great example, BGAs. If I have a very small BGA, a micro BGA, 0.4, 0.5 millimeters, I'm really worried about shorts under that. So I don't want to put too much paste down. I might set my spec limits at 25 to 125% to make sure I don't put too much paste down. Now, on a large BGA, a big plastic package where I'm worried about warpage and head and pillow, I have a wider pitch spacing. I'm not so worried about bridges. I may run that at 75 to 175% just to ensure that I'm getting enough paste out on the corners to compensate for warpage and head and pillow. I cannot compare the two data sets for a CPK that's running spec limits 25 and 125 to one that's running spec limits of 75 to 175. By just looking at the standard deviation as a percent of the average, however, it normalizes everything and it takes the spec limits out of the equation. Typically we look for a CV of 10% or less. The reason we look for 10% or less is because if we go out from our center point, 3 standard deviations, and it's 10% or less, that means we're at plus or minus 30. We've set our spec limits at plus or minus 50, we're in good shape. If the coefficient of variation creeps up to 15%, we could still hold kind of the assumed default tolerance because 15 times 3 is 45, although ideally we definitely want to see it 10% or less. So my advice to people when they begin applying statistics to their print process is the same advice you would give to anybody trying to optimize any process. First, reduce the variation. Get that data distribution tighter. Get that bell curve thinner and taller. So that means you're using the metrics of CP and CV. Then once you get that variation down, you go adjust your average or your mean. That gives you your CPK. That might mean making an aperture a little larger, making it a little smaller, but by all means get rid of the variation first and go after the mean second. So my preference has always been CV because it allows me to compare different data sets and it doesn't have arbitrary spec limits in. CP is a good one, but I have to warn all the users to be very careful about CPKs coming off of SPI machines because many of them are centered at 100. And any shift, even if you get a tighter distribution, can lower your CPK. I know that's a whole lot, so if there's any questions about it, just jump in. And finally, I've got a few slides here, a few tech bulletins showing how the process can benefit from NanoClear, and the next one will show us how you can demonstrate the cost savings. Now, one of the things we found about NanoClear is it's got 3 distinct categories where it can benefit SMT operations. The first one is in quality. We already mentioned that we have higher print yields, higher end-of-line yields, and better transfer effectiveness, which again is different from transfer efficiency because effectiveness looks at the quality of the print and the variation in the print volumes and heights. In terms of productivity, we see less downtime for underwiping and less downtime for paper changes, which can keep your line down for maybe even 5-10 minutes unless you have the automatic changing rolls. And we also see a lot of reduction in cost because we have less rework and because we're using less paper, less solvent, etc. If we just kind of break it out, what I've done here is shown based on whether you look at your PCB by component population density or component mix or component type, where you'll realize the best benefits. You'll see measurable improvement or substantial improvement. So if you're looking at your board in terms of population density, if you've got a high density board, you're going to see substantial improvement and all quality, productivity, and cost reduction categories without a doubt. If it's a lower population density, you will still see measurable improvements. They won't be mind-blowing substantial improvements that you would see on a high density board. Medium density is a bit of a mixed bag. You definitely get substantial improvement in terms of yields and transfer effectiveness. If it's medium density, you're probably not going to see as much improvement in underwiping just because a medium density board doesn't need it as much as a high population density board. But you'll definitely reap the benefits in less rework because a medium density board will have tough to print components on it. Now, if you're looking at components themselves, the mix of components, if you're doing really miniaturized stuff where most component pitches are 0.5 millimeters or less, you're going to see a serious quality improvement, productivity improvement and less rework. Will you use less paper and solvent? Yes, but it won't be as drastic as if you're doing high population density. If you've got what we like to refer to as broadband, a mix of fine and coarse pitch components, you'll definitely see substantial improvement in yields and substantial improvement in reworks, but more modest measurable improvements in terms of productivity and the other quality and cost categories. And if you've got an easy board where most of your component pitches are better than 5 millimeters, I want to come work for you. But actually, you still will see a good improvement in yields. You'll still see a good improvement in underwiping and downtime and paper usage. If your pitches are greater than 0.5 millimeters, you're not going to see a lot of transfer effectiveness except crisper prints, and you shouldn't be making that many defects that require rework if most of your component pitches are better than 0.5 millimeters anyway. Now, if we just look at component type, if we're doing the leading edge miniaturization, again, you're going to get that substantial improvement across the board. If you're working with some of the challenging new packages, if I know right now a lot of people are getting hit with 0.5 and 0.4 millimeter leadless BGAs on 0201s. They're becoming more popular. If you've not used them before and you're having challenges with them now, the nano coating will definitely help you. It'll bring you substantial improvement pretty much across the board. And if you're doing mainstream SMT, which when we're talking BGAs 0.5 millimeter or larger, leaded devices 0.4 millimeters or larger, your chips 04, 02 or larger, you're going to see a measurable improvement. This is really my estimates based on my years of working with this and implementing it in factories. There's no hard and fast data behind it. It's really just empirical and observations, but it's meant to give you an idea based on your own process where you can expect improvements, and it's also meant to help you better estimate in this downloadable spreadsheet how you can demonstrate NanoClear's cost savings. And this is the last bulletin, I believe, so I thank you for bearing with me through all the some of the more detailed and tedious stuff. This cost calculator can be downloaded from the Aculon website, from the banner on my website, and this link will be active when we're done with the webinar. So there's two tabs on this spreadsheet. One feeds the other. So the first tab you want to look at is the cost calculator tab. Now, we did a webinar on this a while ago that you can also download if you want more detailed information. But what you do here is you enter the time for rework, the labor rates, wiper paper information, what it costs for per roll, how many feet per roll or meters per roll, the cost of rework. We have simple rework. I'm sorry, that is my mouse going crazy. I'm turning it off. We ask for simple rework versus complex rework, defining simple rework as something that uses hand tools. Soldering iron, solder, sucker, hot tweezers, braid or wick, cord wire. Complex rework we define as something that requires a machine, an air vac, or other type of BGA or QFN or LGA rework system, because it also requires more time and a higher skilled operator. So we plug in estimated times and labor rates and overhead rates and the cost of wiper paper, the cost of solvent, and what's in these yellow cells here feed into the cost savings spreadsheet. And what the cost savings spreadsheet does is you put in your current yields, what you would expect to yield, and a basic breakdown percentage-wise of your defects being simple or complex. We also look at the productivity, how many times you change a roll per day, how many minutes does it take to change the roll, and the cost reduction. Your cost of simple rework is fed into here from the previous tab. Your cost of complex rework is fed into here from the previous tab. The payback period for coating the stencil is calculated. The annual savings per year reduction, and the amount of extra uptime that you're not losing to paper roll changes is also calculated. So it's You can play what-if games by changing yields, by changing numbers, by changing cost of coatings. No cells in here are locked. The sheet isn't protected, so you can actually use it. In addition to looking at the savings you're going to project by using NanoClear, you can also add in if you want to go to a wiper solvent, or if you want to use a more costly paper because you're going to be wiping less and it'll be more effective. You can play all the what-if games you want, and again, nothing in there is protected, so you can see all the calculations. They're completely transparent, and you can tweak it to whatever your particular scenario is. So that concludes the 12 new tech bulletins. As I said, they will be available online individually, and anybody who signed up for the webinar will receive a copy of the entire presentation. Now I will turn it back to Edward to summarize what I just reviewed.
Great, Chris. Thank you. That was an excellent overview, and obviously a lot of material in that. And once again, I want to emphasize each of these tech bulletins are designed so that you can download them, you can share obviously with your colleagues or with your customers, so that you know, there's a lot of information in each of these things, but it's based on 5 years of experience working with customers and trying to make sure we address today the key questions they have. So so let me start to wrap this up. You know, NanoClear obviously has, you know, been a successful product. It's the #1 nano coating globally. As you've seen in this webinar, there are easy to calculate benefits, whether it's the improved quality or productivity or reduced costs. And as you saw on that last cost benefit calculator, we often find people are getting the payback within a couple of hundred prints. So it's a very quick payback for the NanoClear product. One of the things we like to emphasize, and I think you saw it in the tech bulletin talking about where the benefits come from, is this is not just for fine pitch stencils. Yes, the trend to miniaturization has really necessitated in some cases, you know, people like Qualcomm will only, you know, basically use this on, you know, they mandate that every stencil has to have this in order to get the production. But for those of you who are not on such fine pitch stencils, then there's still some pretty significant benefits as well. One thing we often get, because it's a wipe-based system, is, you know, can we coat the aperture walls? And I think clearly there's a technical bulletin that demonstrates the answer is yes to that. And then the other kind of key question we often get is around durability. And, you know, we've had a lot of success with customers, you know, printing 25,000 or more. But in some cases, if you're using a very aggressive paper, it can damage it quicker. And so, you know, we've given some recommendations here and some types of paper that we'd recommend that, as Chris said, is kind of, if you're on your Teflon pan, you wouldn't use a Brillo pad or a steel wool to clean it. And so in this case, we'd like to see people use a softer wiper paper, and also an engineered solvent we think will also do it well. So clearly this product is available on a global basis. For those of you who are going to be coming to the Apex Expo next week in San Diego, we'll be delighted to chat with you on the stand. We're going to be there on booth 1805, so please stop by and see us. This presentation is going to be emailed to everybody after this, and you'll have links to instruction videos on how to apply it. You can download some technical bulletins. You can ask us questions on that. You can have a look at the cost calculator worksheet. So lots of resources are going to be available to you after this. This is our contact information for those of you who want to email us directly, whether it's Mario, who's the product manager for this category, or myself, or Chris. And let me see if I can bring up any questions that we may have here. So it looks like we've gotten most of those covered. I don't see anything that we didn't cover in a subsequent one. So so with that, we're bang on time. So again, thank you for participating in today's webinar. Your questions have come in from, you know, obviously we're trying to answer customer questions on the applications or technical bulletins. You know, send us questions if you have anything. This is going to be available for download, the broadcast, as well as other resources. So with that, thank you, and thank you, Chris, for doing this, and we wish everyone a good day. Thank you.